So I've outlined the approach to static corrections. It was basically an uphole method with residuals interpreted manually from first breaks in between each shot point, and then an application of automatic statics program in the data processing. Data processing we essentially applied was normal seismic type data processing. By the way, these are all six-fold, these sections, as used in the oil industry. Perhaps the one thing that was very hard to do the first year in particular was to convince the processing centre of actually what we wanted, the accuracy requirements. They had to carefully edit all the data, because it's no good really adding noisy traces in because you don't win. And so it's not just a matter of production type processing. You have to have quite a bit of feedback between the geophysicist and the processing centre, because ultimately a mining machine is going to come along the seam equivalent to one of those events, and a miner's either going to say, well, gee, you didn't interpret that fault, or you put something in here and it isn't there, and look what we've planned our mine accordingly. It's probably a little more exacting than in oil work, where if you side a hole and get a dry well, that's just the luck of the draw, isn't it? One thing that we did find help though was migration. It helped to, even though the dips are very small, it did help to clean up a lot of these small structures. And this is just an example. This is the migrated section and this is the unmigrated section. And I don't know whether you can see it, it's quite small, but you can actually see an event dipping back in there like that, which is probably related to a reverse fault. It's not quite so obvious here. In this case here, you find that this dipping event here is in fact partially the effect of diffraction, and you find that when you migrate it, the thing collapses down and becomes quite a considerably steeper gradient, which would be an important thing for the miners to know about, because grades are probably as important as actual faults. So, putting all that together and drawing a comparison, this is the original data as it was recorded, the analogue data, and the thing to watch here is this event here. And this is the high resolution line over that same, virtually that same geological structure. And that trough I showed you is this feature in here. And it's no longer a trough, it's in fact a very complex series of faults. The actual comparison is here, and in frequencies the dominant period has gone from 17 milliseconds to 7, and you can see the increase in resolution as a result of that. If you actually look hard at this, you can probably see every feature that's on there, but the crunch comes when you've got to interpret them from that data, and you probably wouldn't interpret them without knowing that they're there from that data.
What's the increase in cost?
Well, it's very hard to it's hard to say, because if you compare it with this type of recording, it was so different to this recording. But in fact, very early on in the piece, I did a little exercise to work out how much this stuff actually cost per line kilometre compared to that, and the increase in cost wasn't half. Because with these old single file crews, of course, they had a lot of blokes there in the field, and they had lots of jugs to lay out. A normal seismic crew with lots of groups of geophones and what have you, gee, if you talk to GES, that they use the bare minimum number of blokes compared to some of these, to some of the overseas crews. I think on some of the crews in Nigeria and what have you, I've heard of them having 200 blokes just on the line planting jugs. So that's where the expense comes probably. Whereas with a high resolution crew, you could probably shoot it with a total crew of about 8 blokes, not including the drillers. Well, despite all the care, of course, some uncertainties do still remain. You get things that you're not sure whether they're static jumps or not. You also have features which you see on the slides, which until you know something about the geology, you don't really know how to interpret. These are examples of these type of structures. In fact, since I made up this slide, I probably know what these are. This is probably related to seam splitting, where two seams actually split away. One seam splits into two seams. And this one here is probably more interesting because you get this extra leg introduced in here, and the event has got a slight bow upwards in it. They're actually mining a seam which is probably about related to that reflection in there, and right in this part of the mine they had really bad roof conditions, and fortuitously we've got a borehole down through here, and there's an increase in the sand-shale ratio between the two seams, so it looks as though there's a sedimentary variation in the roof of the seam they're mining, which has caused them to have weight problems, and that's what's caused them to have mining difficulties. Other problems that affect interpretation are the actual orientation of the lines relative to the structure. You have to have a pretty good guess as to which way structures run before you go into an area to try and orient your lines so as to best pick them up. Of course, it doesn't work all the time. This is a slide out of after Anstey, and it illustrates the problem of going across faults at a skew angle. Their effect changes because the diffraction off the edge actually flattens as the angle becomes more acute, until of course if you're running parallel you don't see it at all. And that's an example of data across something which I'm pretty sure is sub-parallel to the line, and you just really can't decipher what's going on in there. So in designing a survey, the orientation and the grid spacing is important in terms of what sort of faults you're looking for. And I'd just like to digress here when we talk about faults, because it's pointless talking about resolving a 3 metre fault, say, if it hasn't got any body, as it were. There are faults at Blackwater which have 3 metre throw, and in one cut through, and cut throughs about 50 metres either side don't exist. And you've got to ask yourself, well, does a fault like that exist to a seismic wave anyway, because it's of such limited lateral extent that even if you could detect a 3 metre fault, because of its short lateral extent and because of the aerial effect of reflections, you probably won't be able to see it anyway in that particular case. And it's quite ridiculous, really, if mining engineers stopped and thought about it, to ask you if you can see a 1 metre fault, despite the fact that we just can't get frequencies into the ground that would allow you to do that anyway. But most 1 metre faults are of such little lateral extent that they're probably not important in overall mine planning, except for other effects which might be related to them. And you probably won't be. Because they've probably got no lateral extent. Well, the proof's in the pudding, and we'll go back and look at the structure from Cook Colliery that I showed you earlier. And this is a seismic section over it. And the major displacement's actually in there. That's actually a statics bust, that particular part of it. And this is a major fault that we knew about in Cook Colliery, but the orientation of it wasn't known at all, and in fact the seismic survey shifted the fault in such a way as it increased the reserves of the colliery, because the mine's over in here and they don't really want to come down in here. But one thing about this fault is that it's not simple at all. It's on two seismic lines that it's stepped. It's got over 100 metres of throw, and on two lines 200 metres apart it has stepped laterally 100 metres, and it appears that this thing's a non-echelon type wrench structure, so you get all these sub-parallel major faults all the way, and you get very complicated structures and things right in the area of that fault. And this is probably the most satisfying one to me because we predicted this one before they hit it. And for a week before they hit it, I had a phone call every day saying we haven't hit it yet, sort of thing. And what was really funny about it was there was a bore out here, of course, that showed only about a metre's difference in the elevation on the seam that they were mining back in here, so they had no indication of it from boring. And until they hit it, and then when they probed out, they actually confirmed the geometry as shown on the seismic section. Another similar one is that a year or so ago, this mine was probing up into an area, and they had a disastrous outburst which killed 2 men. And at the time, there was no obvious geological reason for it. The coal was myelinized in the zone. It was a gas outburst. But there weren't any obvious major structures or things around, except that the seismic section had picked up this little event running through here. And I suggested to them that it could quite easily be related to a reverse fault. And only about a week ago, they went back up into the area and they drilled down into the floor of the seam that they were mining. And 3 metres below the floor of the seam, they intersected another section of the same seam. So we've actually confirmed that interpretation in there as well. And just so we've shown where it works very well in that area where we can control the statics and the surface problems aren't too hard. We tried it in an area where the surface problems are much more difficult. And had soft tertiary sands and clays and surface basalt on it with the Permian coal seams beneath. And that's the sort of section we got out. And really doesn't mean anything. In another area in New South Wales, we took it across a section of outcropping coal seams. And the seams in this area, it was known that the coal seams dipped up to the surface at outcrop, but there wasn't really any confidence that it wasn't related to faulting rather than just a monoclinal structure. And certainly the seismic across the structure proved that it was monoclinal rather than being a lot of faults, except there probably is some faulting in here around the axis. But if you look at the time scale on that, that's only 0.1 of a second, so you're right up very shallow in there. And these are all the events of the coal seams coming up to outcrop. I'll just put this slide back in to show you the comparison once again. So we've actually got the method now as a viable method, certainly in some areas in Queensland, and I know there are areas in New South Wales where it will be viable to use as a mine planning tool. And we don't really have to bend over backwards to sell it to the mining people anymore. I think in the future there's still potential to improve the method. You could go to the costly measures of putting detectors down below weathering, but that would necessitate a lot more drilling, which of course is a major expense. There's a possibility you might improve it by just putting your detectors down rather than a foot. If you put them down 10 metres or something, you might get an improvement, I don't know. Other areas that we could look at are more advanced types of processing. This is all fairly standard. If I just show you I'll just digress back for a minute and point out the problems with coal measure seismic work. In most high frequency work you're battling attenuation because attenuation is measured in decibels per wavelength as a more often than not, and of course with high frequencies they have more wavelengths before you get to a depth before the low one, so they get much more attenuated. So apart from the fact that you're battling that form of attenuation, coal seams themselves are very gassy and they're very low velocity, sloppy things, and they undoubtedly have a very large attenuation factor themselves. Added on to that, you also have the problem of interseam peg leg type multiples, which have been shown assist in the propagation of energy through the of seismic energy through rocks. But in fact, they lower the apparent frequency of the wavelet, so because you get more and more little events added on afterwards to the primary reflection. And of course, in coal, we've got such a high reflection coefficient; these things become quite important. So, high frequencies are very rapidly attenuated in coal sequences, and this illustrates it because it's a fairly bland succession of sediments up in here. This is without any filtering at all, and you can't see the top of this, but this is filtered with a 120 Hertz low-cut filter. And you can see that the bottom coal seam is virtually disappeared in that frequency band. There's still quite a lot of high frequency in that because it's got a bit of still got quite a lot of character, that event. So there's still quite a lot of high frequency above it, but we haven't managed to get any of it through. Of course, the other problem is that the high reflection coefficient means that your energy just drops off really quickly. So the hope of ever getting high frequencies into a multi-seam situation and penetrating right down is looks very remote, unless you actually get down a mine and work in a seam down in the succession and look deeper down. And I'd make a point that there was a paper that was presented a couple of years ago by one contractor where he showed some brilliant high frequency sections. Without any doubt, I've never seen sections like it. But he drew coal seams all over them, and there's just no way you could record that type of data in coal measure sequences where you've got more than a couple of seams. And probably the aim of high resolution data is to try and get as much structural detail on the shallowest events you can, because you're going to be physically limited if you go down into the section any further. The other thing about coal seams is that they are a classic low velocity thin layer, and this is the WDES diagram that Red showed you before. And of course we've got you get the two wavelets that interfere until they get down to the the tuning thickness, and below that the only variation you see between you get a composite reflection, and below that the only variation you see is a drop off down in amplitude. And in fact, WDES indicated that you could still get a sizable reflection from a bed that was 1 in 40, which was 1/40th the wavelength thick. That of course depends on the shape of the wavelet that you're using, which in this case is a very simple one, and also on the noise conditions, whether you could actually see that. And this is that effect. It's very similar to the one Red showed before, where you get the two resolved and they come down to the tuning thickness. And theoretically, anyway, if you just look at simple wavelets, down into about here, you can distinguish the reflection from the top and bottom of the bed. But once you get into here, the whole variation is shown in amplitude rather than in anything characteristic that you can characterise about two individual reflections. This is just the WDES thing again, where you get this is out of that Sheriff volume on seismic stratigraphy. And it's just a simple model which indicates a trough related to the top of the unit and a peak related to the bottom. And as you go in, you get into about here, and under these ideal noise conditions, you can actually still distinguish something from the top and bottom. But once you get over into here, it just becomes an amplitude effect. In the real world, it's probably somewhere out here where you can actually distinguish between the top and the bottom. But the amplitude effect does open up an interesting possibility in that if you put a fault in the on a coal seam, then because the reflection is actually a composite, it's probably more subject to amplitude change than a normal reflection is across a fault. And you may in fact be able to see quite subtle structures down to the size of seam thickness throw, as long as they've got a reasonable lateral extent, by looking at the amplitudes. And I put this one in because this is a section which has got very little amplitude adjustment on it, and you can see, well, we know there's a fault in there, and there's quite a substantial amplitude bald zone in there, and there's one there, but the other one that's really interesting is this little one in here, because that's really quite subtle, and on the final section, which had all the amplitudes adjusted up, you could hardly see that. In fact, I think I've got a diagram of it later on. This is a similar effect. That's virtually the final section where the amplitudes have been adjusted up to give a balanced looking section. This is one where the amplitudes have been maintained, and you see in here you get a change in amplitude, and in here you get a change in amplitude as well. Now that is a long strike from this thing in here, which is quite a substantial block structure. So it's a structure which along its length is actually dying out in terms of throw, and when it gets quite small, you'd be lucky to see it on that section if that was all you saw, but on that section you can still pick it quite well. Another interesting thing is the just in the display on the final sections and how you can see these things. This is a section plotted at normal polarity, and you'd say, oh well, yes, you can see the fault there because it's got a character change in there, but there's no displacement at all on the top leg. But when you plot it in reverse polarity, it's quite obvious, and that's a fault that we know about because the mine stopped on it, and we've got it on a few lines. So resolution depends not only on what you get into the ground, but how you handle it later. And I think something that is overlooked, and particularly overlooked in these days of electrostatic plotters, is presentation of intermediate stages of data is really important. And ultimately, the final filter is this eye, and if what you have isn't pleasing to the eye to interpret, well, you may as well shut the whole thing up and go home. Right, that's it.
Talk of Phil's obviously expresses a lot of extremely good experience in this important problem.
Phil, I'd like to make a comment on one aspect of this high-resolution seismic, which I think has a very important bearing on resolution, also on statics and your criteria for eliminating surface arrays, and that is the Fresnel zone effect. I've just done a quick calculation here for one of these Leichhardt sections, and I get a diameter of the first Fresnel zone of around about 80 metres, which is quite considerable compared to your spread length. And I think the only way that you're going to be able to overcome that problem is a migration before stack, so that you can get back down to, or downward continue the wave field back to the actual reflectors.
Well, I think that, of course, that amplitude baldness across those faults is of course related to the diameter of the Fresnel zone. One thought that crossed my mind, and I haven't really thought this through, is that maybe thin layers have a different area of a Fresnel zone than just an ordinary reflection because of the interference of the reflection from underneath. I don't. It might be smaller in diameter. I don't know. I haven't really considered that, but certainly, yeah, I take your point. That is a real problem. Of course, the other problem with the Fresnel zone too is if you look at a seismic section, you assume that everything's in the plane of the section, but in fact, if you go fairly close to a structure, it only has to be within half a Fresnel zone or something diameter from the line, and you get an effect due to it, of course.
May I ask you another question too? You mentioned the work that was done in the UK on the use of small charges to try and push out the high frequency end of the spectrum. Have you taken experimental data yourself that's confirmed this cube root law of spectral amplitude? Because it seems to me it's rather extreme that you're talking about a 6 dB increase in signal by increasing the charge 8 times.
Yes.
Which is quite small. I think that, at least on the case of, that's for a pressure pulse in a spherical cavity, but if you do the calculations for that in a cylindrical cavity, it works out to be proportional to the mass. So it's quite a substantial increase in amplitude, which would be more in line, I think, with normal observation.
Yes. Yeah, I think that that we have done some work with charge sizes, and I think that one of the main reasons we did the work was because if you pick a small charge, you go along the line every now and again you miss one because you just don't couple the energy adequately. The greatest advantage to me seemed to be that you didn't generate as much random shot noise with the small charge as you did with the the large one. That theory of Anton's is all very well in theory, but crikey, the charge is only the size of a penny bunger, and you're putting it in a 4.5 inch hole, and you can load the thing. You can reload the hole after you've shot the thing off, because there's no such thing as an equivalent cavity in the rock. So obviously other parameters play an important role other than the old spherical cavity idea. The increase wasn't drastic though, that's for sure.
You mentioned that contractor who produced a section that had reflections all through the sequence. Do you think that was just a case of very severe narrow band filtering?
Well, he had the detectors below weathering, and I think that's where he really won, because your normal attenuation is between 0.5 and 1.1 dB for wavelengths, but I think they've measured up to 30 dBs for wavelength in weathering. And the other thing, of course, is that most Europeans, when you say your weathering's 20 metres thick, their sort of jaw drops on the ground to start with. So it's probably more realistic to put shots below weathering in some of their areas. The thing, of course, in this area is that in the shot holes there's not even any water in them. The up holes indicate that the base of seismic weathering is actually where we're putting it, in the unweathered rock, but there's no actual free water in the holes. We have to put water in the holes to assist with coupling. It's probably because they're probably saturated but impervious, so you're not getting any, they don't make any water.
I'm just wondering what sort of a record do you get over the mine workings at all, and is that correlated or correlatable to the sections?
Well, if you consider mine workings, they normally only, in first workings, they normally only take out about 30% of the coal anyway. And there's an example in Waters, I think, which shows a seismic section over coal mine workings. And because of the Fresnel zone effect that Stu's already mentioned, you can't see reflections from individual roadways or anything. But by putting air in at 30% of the seam, you effectively increase the reflection coefficient, so you see the effect as an increase in reflection coefficient. Now, we don't really have a great deal of data over workings that are extensive enough to give you an effect like that. The attitude is, of course, that we know what's in the workings anyway. We're trying to find out what's away from the workings, and when we went across structures that were known in the workings, we went across them to try to be as far away enough from the workings so that we knew that they wouldn't have an effect. There's another good reason why we didn't go over the working zone, that is because most of these mines haven't developed very far, and you'd have to put a line through the manager's office or something to go over the workings.
It's only penny bunkers.
Yeah, Mayhew isn't though.
It's on.
Tom, what I want to ask you, Phil, was you said you were using the first arrivals for static creases. Did you shoot a separate surveys for that, or did you just use the reflection?
No, we didn't, because we had an uphole at each fourth geophone point. Well, the way we shot it in effect was to put the shot point on the geophone station, and that way you get an accurate uphole time at every fourth geophone station. Then we only use the first arrivals. We use the sort of a delay time method to correct for the residual weathering corrections for the intermediate stations.
One other question, that diagram you showed of the Cook Colliery block folded thing.
Yeah.
What was the sort of wide dimension of that? You said it was about 20 metres that way, sort of thing.
Yeah, the actual width of the fault was about 20 metres, and in length it runs for quite a substantial distance. So it runs for about a kilometre, I suppose, back to another fault, because we've got it on quite a number of lines. But we do certainly have picked fault blocks similar to that that are very much smaller. We had one that was only about 10 metres wide, and we still actually observed an effect from it. And it could be related, of course, on those structures. They've probably got a diffraction coming off the downturned end of it, so so it probably exaggerates them somewhat.
Phil, with the short strike extent of some of these faults, how do you work out your grid size?
It comes down to economics ultimately. I think with the first pass of Cook Colliery, we actually spaced the grid with a staggered grid. We had two lines 200 metres apart, then a gap of 400 metres, then 200 metres, just to try to get a feel for what they were doing. And then last year we actually came back and filled in the intermediate lines, but ultimately it comes back to how much you're prepared to pay and economics. So I guess you would say that we've used 200 metres to date, and that's been more an arbitrary selection. But most of the structures that are significant do have a strike length over a couple of 100 metres, but in this particular area they go around corners and do all sorts of things. We're about to launch on a major exploration program with Seismic in the Blackwater area to find a new mine, and what we're doing there is we're doing it on a kilometre grid. The idea being that we worked out the size of a mine area, which would be 60 million tonnes in situ or something or other, and then we worked out if we did a kilometre grid, to get a mine area we would have at least 6 lines over any one area that would constitute a mine, and that would give us a feel for where the major currents of structure was, and then to prove up that mine area we'd come in and fill in on much closer line spacing. People always ask me how much it is a line kilometre, and it is expensive. If you talk about it in terms of one survey, it costs a lot of money. But if you work it out, let's say it's in the vicinity of $5,000 to $10,000 a line kilometre between the best and the worst. If you prove up a line with no faults in it, that's quite a lot of coal. That's a kilometre long. And the other thing that people have to remember is that it's there forever, and you can always go back and look at the seismic sections if you do encounter a fault later on, and you should be able to, as you get a handle on things, you should be able to put a limit on anything they've encountered in the mine, and if it is up or down, you'll probably be able to pick that even, and be able to tell them where to go up or down or whatever.
Can you tell us what your timetable is, Phil, for three-dimensional work?
Yeah, well, it'd be nice, wouldn't it? The trouble is at 10 metre spacing, I mean, mind boggles at how many...
Well, the Germans afforded it once, didn't they? I wonder what it cost them.
Yeah, the German approach was probably a little somewhere in between what we've done and the early stuff. But where they actually did their three-dimensional work, they had the Rhine River and they put the spreads out either side, and they actually used a seismic boat in the river, letting off the charges. They reckoned with that Prackler method, the way they did it in the Raw, it was $30,000 a square kilometre, I think, but I can't remember what the interval was. It'd be more than that now. But over a shaft side, of course, you might be able to justify that. Justify one at a 3D survey.
Well, if I were David King and we were approaching the end of the videotape, I think I'd start to get a little nervous. So I have to thank Phil again and give David. Should we switch off for a minute?